You know I'm too generous. Now I've learned to never help you out. 'Cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now. 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 You cashed in on my promises. You know I'm too generous. Never help you out. 'Cause I'm done cleaning up your mess. Found myself in my regrets. I've become a little stronger now. A little stronger now. Casting on my promises. You know I'm too generous. Now I've learned to never help you out. 'Cause I'm done cleaning up your mess. Found myself in my regret. I've become a little stronger now. A little stronger now.
Open eye, feel the waves cut through me. Hypnotized by the sounds I'm breathing in.
Bom dia a todos e a todas, meu nome é Gustavo e eu vou ser o host da missão de hoje. O lançamento de hoje vai ser a missão Xrism and Slim. O seu destino é a órbita lunar. Esse lançamento ele vai ocorrer com o lançamento H2A-202, desenvolvido pela JAXA. A JAXA é uma empresa aeroespacial desenvolvida pelo governo japonês.
Good morning, everyone. Today we will be live streaming the launch of Xrism X-ray imaging and spectroscopy mission and SLIM, the small lander for investigating moon. This live stream is made in Japanese and in English globally. Good morning, hello, and good evening to the audience in the world. Please enjoy watching until the end of the live streaming. I will be your MC today. I'm Shintori Umi from ISIS JAXA. My research area is solar physics. Hinode satellite of JAXA is used in my research, and I'm also researching and developing solar sea. Today, at long last, Xrism and SLIM will be launched. After postponements, at last today, there will be a launch, which I look forward to very much myself. In a special studio here in Sagamihara, to communicate to you the launch this time, we have experts from projects. They are the world authority in each respective area. Let me introduce them. First, Professor Kyoko Matsushita from Department of Physics, Tokyo University of Science, who is also the Xrism project scientist. Professor Matsushita, thank you for being with us. Thank you for having me. I am Matsushita. I am a Xrism project scientist, and Xrism scientific observation is an area that I'm involved in. Usually, we are surveying the cluster of galaxies, and I'm looking forward to having data. Last time, unfortunately, due to weather conditions, launch was postponed. I hope weather will permit the launch today. Thank you. Next, Dr. Megumi Shidatsu from Graduate School of Science and Engineering, Ehime University, who is also a member of Xrism Science Operations Team. Dr. Shidatsu, thank you for being with us. Thank you for having me. I'm Shidatsu from Ehime University. I'm a member of Xrism Science Operations Team. I process data so that users will be able to use the data from the satellite easily. Usually, I conduct the research of black hole. In my daily research, using Xrism, what new understanding will be obtained about black hole is another thing I look forward to. Thank you. And from SLIM sides, we have two specialists. First, Professor Osamu Mori from JAXA, who is SLIM project member. Professor Mori, thank you for being here. Thank you for having me. I am engaged in development of propulsion system of SLIM, and I'm also a member looking into the future project of lunar exploration. As we consider future lunar exploration, I made keenly aware that the technology used in SLIM will be quite essential. I hope today's launch will be a successful one to mark a new step. Next, we have Professor Makiko Otake from Department of Computer Science and Engineering, University of Aizu, and SLIM Payload Manager. Professor Otake, thank you for being here. Thank you. I'm Otake from the University of Aizu. I'm a payload manager. To maximize the outcome obtained from SLIM, I'm involved, and I'm also involved in development of observation instruments. Usually, from the lunar surveillance data, I conduct a research of geological material on the moon. About the SLIM launch, as a researcher, I'm very excited. Thank you very much. We have 4 experts here, and we will hear more from them later.
Now, I would like to introduce the mission today. But first, let's see how it looks like at the launch site. This is the scene at Tanegashima Space Center. And the vehicle itself has been transferred to the launch pad. As you can see, the weather is fine and moderate. So I would like to share with you the flight route and the sequence. The Xrism and SLIM are going to be on board on the vehicle. What characterizes the liftoff is going to be the 2-stage one. That's what characterizes the flight. The liftoff will be at 8:42:11 seconds. After liftoff, at 1 minute 30 seconds, the solid fuel booster will burn out, and 50 seconds later, it will be separated. At 4 minutes and 10 seconds, the upper fairing that contains Xrism will be separated. And after 6:30 seconds, the second stage is going to be changed. And 30 minutes later, the second stage is going to be suspended. And 14 minutes and 30 seconds later, at 8:56:32 seconds, the Xrism is going to be separated. And after 17 minutes, the lower fairing is going to be separated. And this is going to be inertia operation. And 44 minutes after the liftoff, there's going to be the ignition of the second stage. 2 minutes will be used for the combustion. And at 9:29 seconds, 50 seconds, 47 minutes, 39 minutes after liftoff, the SLIM is going to be separated. It will be 8:56:32 seconds. That is the separation of the Xrism, and then the SLIM separation will come at 9:29 minutes 50 seconds. I would like to ask a question of Dr. Mori, and it was originally scheduled in August, but 12 minutes later because it's been postponed. And at the original plan, 9:34, that was the launch time, but 45 minutes earlier this time around for today. What is the reason behind this? This is related to the SLIM's orbit. And please allow me to give you an explanation. This is the mock model of the SLIM, and this on my left hand is the Earth. So it is going to be inserted onto the orbit of the circulation, and at appropriate timing, it is going to depart the orbit and to reach the moon. And the timing of the departure should be set at the same timing. Therefore, it is going to be inserted onto the orbit. Despite the liftoff day, it has to be the same timing. And that is the requirement. On the other hand, the Earth rotates around the Sun, so it moves day by day. Therefore, at the same time, if it is going to be launched, the orbit itself is going to be changed a little bit. Therefore, in order to put it in the same orbit, it has to be launched 4 minutes earlier. Therefore, 40 minutes earlier every day. Therefore, 12 days delay. Therefore, in total, about over 40 minutes and should be made earlier. And that is how the scheme is. Thank you very much. The SLIM has to go to the moon, and the orbit itself, the route itself, has to be the same. Therefore, the timing of the liftoff have to be synchronized with that timing. However, the Earth itself moves constantly, and therefore it should be the timing for inserting the vehicle, the satellite, into the prearranged orbit. So there was a change. Because of this delay or postponement, does it have any impact on the satellite? There is no problem with that. Thank you very much. There was the postponement, but that was because of the strong wind in the sky, and that did not fulfill the requirement. The vehicle itself has not no problem. Therefore, when it comes into the postponement, we had to stay on the safe side, so that we will be able to have a decision today and to make a launch. Thank you very much. Now, I would like to introduce the Xrism satellite.
We have a video message from Xrism project manager. So please take a look at the video message as well as video clip introducing the project. I'm Maejima, Xrism project manager at JAXA. The satellite that we developed will be launched at long last. Xrism was developed under the lead of JAXA jointly with NASA, ESA universities, research institutes, and companies in and outside of Japan. Sagamihara site is fully prepared to operate Xrism. The leading-edge mission instruments are on board the satellite. With these instruments, X-rays from celestial bodies will be observed to elucidate the structure of the universe and the mystery of its evolution. Stay tuned for the observation by Xrism.
My name is Lillian Reichenthal, and I am the NASA project manager for the X-ray imaging and spectroscopy mission named Xrism. We are incredibly proud of our close collaboration with JAXA on Xrism and are very excited for the upcoming launch. Together with JAXA leadership and the accomplished engineers and scientists at both JAXA and NASA, the team was able to build and deliver an X-ray calorimeter spectrometer named Resolve. After undergoing a comprehensive ground test program in Japan, the instrument performance remains stable and is excellent. The spacecraft testing is complete and the team is prepared for mission operations. As we are looking forward to the launch and the long-awaited science on Xrism, I wanted to commend our JAXA colleagues for their hard work and relentless dedication in overcoming the challenges throughout development and test on Xrism. Xrism is going to provide us a view of the universe in more detail than ever seen before. The work on Xrism is just beginning, and we are very excited to get started.
Video was very cool. The first video was a video message from Maijima-san, JAXA project manager. The second message was from Dr. Lichtenthal, a NASA project manager. Maijima-san said that Sagamihara is fully prepared, and he sent a strong message to stay tuned. From audience, we have a question about Xrism. Professor Matsushita, would you like to take this question? NASA's Dr. Lichtenthal mentioned in her message that Xrism is a mission that has international participation. Yes, that is correct. With the NASA of the United States, we have worked over many years to develop satellites. This time from Europe, ESA is participating, and from not only NASA in the US, we also have participation from Canada. More than 100 scientists are participating in the team, and including engineers. The team is very large. That's fantastic. A very large number of people are involved in this huge mission. Yes. And the second point, maybe Dr. Shidatsu, could you take up this question? In the beginning of the video, there was a test of the satellite. What is the size of the satellite?
The length is 8 meters long and 2.3 tons and 9 meters width, and the solar panel. So 8 meters long. It looks like a microbus size. And with the solar panel, the width is going to be 9 meters. It is extremely huge, right? Thank you very much. And there is another question, Dr. Matsushita. And it is going to be the X-ray spectroscopy mission. And what we will be able to see with the X-ray machine. 1,000,000 degrees in temperature, huge, very high temperature object, 1,000,000 degrees. It looks like relatively low in our own terminology. So if it is going to be tens of billions temperatures, the gravity is going to be extremely important. With heavy gravity, the temperature goes up. And for example, that when it comes into tens of millions of degrees, how the black hole will emit the wind from the core, we will be able to see it. We are really looking forward to that. So tens of millions of degrees and the celestial objects and very high temperature objects will be analyzed. And on top of that, most of the elements in space are not stars. But when it comes into those high temperature, most of them are gas forms. So we will be able to see the essence of the space.
Professor Matsushita, this is a JAXA X-ray Astronomy Observatory, and I believe you have conducted research using X-ray astronomy with the launch of new Xrism satellites. In comparison to the past satellites such as Asuka and Suzaku, Hitomi, and this time Xrism satellite will be launched. With these various satellites, now that we have new satellite, what do you look forward to? I wrote my doctoral thesis with Asuka many years ago. X-ray color and energy can be measured in very precise fashion. That is what is new about Xrism. Light Doppler effect can be used. Several tens of kilometers per second, such velocity can be captured. So I expect that we will be able to take a look at the new world. Thank you. By using X-ray, superhot gas, the velocity of the movement of superhot gas can be captured. Yes, so that is what is fantastic about this new satellite Xrism. What about Dr. Shidatsu? You are a member of the operations team, and what do you expect from Xrism? Yes, I'm a member of the operations team. After the launch, in the initial 3 months, we will be processing data and we will be validating satellite systems. I will be involved in part of that activities. So I will brace myself so that observation will be successful.
So that means for the next 3 months, you are going to be very busy as a team member. at Sagamihara and station and center, you're going to get involved? Yes, here at Sagamihara, the data is going to be analyzed. So I'm going to move around different places. And at the previous media coverage, the live coverage that you came over to our place, and thank you very much. I hope that we would like to move on to the next stage of this mission. This is about Xrism project. We still have more to talk about, but later on we are going to come back to this topic. But we have to switch the camera to Tanegashima Space Center.
It will be, we have some more time. We have received more questions about Xrism. We would like to address these questions. One of the questions is,
打ち上げ作業関係者に向けて打ち上げ準備状況の報告をいたします。
This is a report of the status of launch preparation from Takesaki Launch Control Center at JAXA Tanegashima Space Center.
H2A ロケット47号機打ち上げ最終実施判断の結果は GO です。
We have just given the final go decision for the launch of the H2A launch vehicle number 47.
現在各系ともロケット打ち上げの最終作業を実施中です。また警戒区域の安全が確認されており、気象条件も打ち上げに支障のないことが確認されました。
All systems are now in final operations. The restricted area has been vacated, and the weather is confirmed to be sufficient for the launch.
従いまして、X 線分光撮像衛星クリズム、小型付き着陸実証機スリムを搭載した H2A ロケット47号機の打ち上げを本日日本時間の午前8時42分11秒に実施します。
Consequently, we proceed with the countdown to the launch of the H2A launch vehicle number 47 with on boards Xrism and Solim, and the launch time is set to be 8:42 and 11 seconds a.m. Japan Standard Time.
機体は最終的な確認作業が続けられており、現在のところすべて順調との報告を受けています。
Our launch site operators have given reports that the final checks are underway, and all operations have proceeded as scheduled so far.
打ち上げ8分前より打ち上げに向けた秒読みが開始されます。
We will start the terminal countdown at T-8 minutes.
480打ち上げ8分前です。現在各系ともロケット打ち上げの最終作業を行っています。また警戒区域の安全は確認されています。
It's 8 minutes to the launch. All systems are now in final operations. The restricted area has been vacated.
460、59、58、57、56、55、54、53、52、51、450。440。
Como já comentado antes, nós estamos ao vivo
29、28、27、26、26、25、24、23、22、21、420、19、18、17、16、15、
安全系準備完了。
13、
The safety system is go.
410、409、408、407、406、
車両系準備完了。
404、
The range
403、
system is
402、
go.
401、400。
Como já comentado como antes,
390、
nós estamos ao vivo para Twitch e para o YouTube. O lançamento de hoje tem como destino a órbita lunar.
380、
O nome do foguete, o lançador, é H2A202. A família dele é a H2 e a sua variante é a 202. Ele tem um comprimento de 53 metros e um diâmetro de 4 metros. O seu custo de lançamento é de cerca de 90 milhões e a sua massa
打ち上げ6分前です。現在、車上の天候は晴れ。気温摂氏28.6度。北の風
e a sua massa é 285 toneladas. A capacidade para órbita baixa é de 10 mil quilos e a para
It's 6 minutes to launch. The current weather at the launch site is fine. Temperature is 28.6 degrees Celsius and wind is 5.5 meter per
330、
second from the north. The weather has no constraint for the launch.
本日の打ち上げ予定時刻は日本時間の午前8時42分11秒です。
Today's scheduled liftoff time is 8:42 and 11 second a.m. Japan Standard Time.
310、309、308、307、306、305、304、303、
衛星系準備完了。
301、300。
The satellite system is go.
290、89、88、87、86、85、84。
Faltando cerca de 4 minutos, o lançamento está previsto para ocorrer às 8 horas e 42 minutos BRT, fuso horário GMT-3. Esses horários eles pegam praticamente para todo o Brasil, ou resumindo, horário de Brasília.
自動カウントダウンシーケンス開始。
The automatic countdown sequence has been initiated.
現在ロケットの管制は吉信発射管制塔から行われています。
The H2A launch vehicle is now operated under the command of Yoshinobu Blockhouse.
250、49、48、47、46、
Se você quer ver mais informações sobre esse lançamento, é só acessar nosso site oficial. Para o pessoal que está na Twitch, vai estar no chat, e para o pessoal que está no YouTube, vai estar na descrição e também na aba sobre do nosso canal do YouTube. Caso você queira achar com mais facilidade, é só abrir o Google e pesquisar por Nasdaq Tech Drive, tudo separado bem certinho, que vai aparecer a gente no nosso site oficial. Lá você vai poder acessar todas as informações sobre o lançamento e os replays das outras missões que ocorreram, como a de Taya e Starlink 612.
200、 190、89、88、87、86、85、84、83、82、81、180。
打ち上げ3分前です。
It's 3 minutes to the launch.
全システムの電源が外部から内部に切り替えられました。
170、
The power has been switched to the internal systems.
1段液体水素系準備完了。
The first liquid hydrogen system has been pressurized.
150 140 39 38 37 36 35 34 33 32 31 130 29 28 27 26 25 24 23 22 21 120 19 18 17 16 15 14 13 12 11 110 109 108 107 106 105 104 103 102 101 100 99 98 97 96 95 94 93 92 91 90 89
O pad já está sendo resfriado e a gente tem aqui, agora a gente tem as imagens ao vivo do complexo de lançamento Yoshinobu LP1, que fica no Centro Espacial de Takeshima, no Japão. Faltando agora 1 minuto e 10 segundos para o lançamento.
The torches are ignited.
59 58 57 56 55
The cooling water system for the flame deflector has been activated.
50 49 48 47 46 47 45 44 45 46 47 42 41 40 39 38 37 36 35 34 35
ウォーターカーテン散水開始。
31
The sound suppression water system has been activated.
27 26 25 24 23 22 21 20 19 18 17 16 15 14 13 12
フライトモードオン。
10
The flight mode is on.
同様電池起動。
The thermal batteries have been activated.
全システム準備完了。
All systems are go.
メインエンジンスタート。
The main engine ignition.
SRBA 点火。リフトオフ。
Solid boosters are ignited.
Lift off。プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H2A has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
60
打ち上げ後1分が経過しました。
It's 1 minute into the flight.
70
ロケットは現在東方向の太平洋上へ飛行しています。
The H2A is now flying above the Pacific Ocean to the east.
83 84 85 86 87 88 89 90
SRBA 燃焼終了。
Solid boosters have burned out.
110
SRBA 分離。
12
Solid boosters have been separated.
15 16 17 18 19 120
1 小笠原局でのロケット追尾が開始されました。
Ogasawara Station has started tracking the H2A.
第1段エンジンの燃焼は正常、制御系、飛行経路も正常。ロケットは順調に飛行を続けています。
The combustion of the first stage engine, true control, and the trajectory are all nominal. The H2A flight is on course.
現在のロケットの高度は約 48km、148km、秒速約 1.9km です。
Current altitude of the H2A is about 148 km.
上部衛星フェアリング分離。
The upper payload fairing has been jettisoned.
como visto antes, a gente consegue ver que na trajetória esperada, ela faz uma curvinha assim para um dos lados. E essa curva, ela é realizada pela seguinte questão: por questões de segurança, os foguetes geralmente não podem sobrevoar locais que tenham, no caso, moradias,
打ち
porque
上げ
se
後5分が経過しました。
It's 5 minutes into the flight.
Porque se ocorrer algum problema com o foguete, algum tipo de abordagem no meio de voo que a gente já teve com um foguete que foi o Vega-C, se torna mais seguro de realizar a abordagem e caso que ele acabe fugindo da trajetória. Aí você tem um local seguro onde não vai cair casa, onde não vai, o foguete não vai cair em cima das casas. Isso daí é uma das questões de segurança. Geralmente, como a gente pode ver, os pads de lançamento, plataformas de lançamento e centros espaciais, eles ficam perto do mar. Só a CASC e a Roscosmos que ignora meio isso. Um dos grandes problemas que a gente tem é até a CASC também, alguma dos estádios eles acabam descartando de forma incorreta. E a gente já teve até casos que a gente acabou dando até uma analisada nas imagens, que alguns estádios foram parar perto de vilas, onde podia ter caído em cima de casas. No lançamento Luna 25, um dos boosters, ele caiu perto de uma mata, caiu numa mata no caso, e uma das árvores atravessou, no caso, o tanque do foguete fora e fora. Não ocorreu nenhuma explosão, mas esse booster acabou caindo na mata. Essas são as duas empresas que acabam ignorando esse meio que procedimento de segurança. SpaceX, NASA e as outras empresas aeroespaciais, elas seguem da mesma forma como a JAXA está realizando. Essa curva é realizada por praticamente todas as empresas para evitar que a trajetória passe por cima de locais onde tem habitantes, pessoas, que qualquer problema pode acabar gerando risco a diversas vidas.
ち上げ後9分が経過しました。
It's 9 minutes into the flight.
Constando também alguns lançamentos próximos que a gente vai ter. Um exemplo que a gente tem aqui é a missão Galactic 3. A missão Galactic 3 é da Virgin Galactic. Para dar uma clareada na mente do pessoal que está meio de fora, é uma das empresas que utiliza um dos lançamentos comerciais mais diferentes do que o padrão que a gente tem hoje em dia. Seriam 2 aviões. Primeiro, um avião ele vai decolar com outro avião embaixo, onde vai estar os astronautas. E como ocorre? Quando o
打ち上げ
avião
後
ele
10
tiver,
分が経過しました。
It's 10 minutes into the flight.
quando o avião ele já estiver no ar a uma certa altitude, o estágio onde tem os astronautas, que seria um avião de menor tamanho, ele vai acabar ser solto e vai ativar um dos seus motores. Após, ele vai fazer uma orientação para cima, fazendo com que ele chegue ao espaço. O que acontece é que ele não fica no espaço por muitos minutos e não é um lançamento muito parecido com o que a gente tem como a SpaceX e outras empresas. A Virgin Orbit, que é uma das empresas que acabou praticamente falindo, ela utiliza ela utiliza uma forma de lançamento meio semelhante. Só que a Virgin Orbit ela levava em um avião uma carga num lançador, no caso o Launcher One, na sua asa, depois soltava e ativava os motores. A Galactic 3 é a terceira missão comercial da Virgin Galactic,
第
relembrando
2
que
段エンジンの燃焼は正常、制御系飛行経路も正常。ロケットは順調に飛行を続けています。
The combustion of the second stage engine, true control, and the trajectory are all nominal. The H2A flight is on course.
現在のロケットの高度は約 552km、秒速約 6.0km です。
Calling altitude of the H2A is about 552 km and velocity is about 6.0 km per second.
esse é um dos lançamentos suborbitais realizados pela Virgin Galactic, mas a Virgin Orbit ela realizava os lançamentos soltando essa carga e depois ativando o motor. Alguns lançamentos acabaram dando errado, infelizmente acabaram dando errado, e teve uma perca total da carga. Esse tipo de lançamento é um lançamento privado, e ele tem a quantidade de estágios de um estágio, no caso, e um comprimento de 18 metros, não é muito grande, e um diâmetro de 8,2 metros. A sua massa de lançamento é uma massa muito pequena, é de cerca de 9 toneladas, o empuxo total é de 310 kN. O local de lançamento vai ocorrer na Spaceport America. Ele já teve 81 lançamentos. E, como eu tinha explicado antes, o avião ele decola. E após, quando chega numa certa altitude, ele solta o estágio onde estão os astronautas dentro. E após, ativa o motor.
第2段エンジン第1回燃焼停止。
The second stage engine cut off for the first time.
Ativa os motores e deles conseguem ir para o espaço. Eles não ficam muito tempo. É um lançamento legal, porque é algo diferente do que o padrão que a gente sempre vê. A gente tem lançamentos da missão Starlink que são rotineiros. A SpaceX ela já tem só na Twitch, em uma das playlists, porque a gente divide todos em playlists, a gente tem mais de 50 horas só de lançamentos da SpaceX. Isso que a gente começou há cerca de um ano. Então, é vamos dizer, um bom tempo que eles têm só com missões.
XRISM 分離
Xrism separation.
XRISM の軌道への投入を確認しました。
Xrism has been inserted into the orbit.
ロケットはこのまま完成飛行を続け、まもなく小笠原局の受信範囲を離れます。
The H2A is in a coastal state now, and shortly it will proceed beyond the tracking area of Ogasawara Station.
次のイベントまで一旦実況放送を中断いたします。打ち上げから約47分後にスリム分離を予定しています。
The separation of SLIM will occur in about 47 minutes into the launch. Until the next major event, there will be an intermission.
竹崎総合司令塔からの実況放送は午前9時25分頃に再開を予定しております。
This live coverage will resume at about 9:25 a.m. Japan Standard Time.
Agora nós podemos ver a curvatura que tem em questão da órbita.
We are watching the live coverage of the launch sequence. Xrism is separated. We have received message videos, so please take a look at them.
I'm Richard Kelly from NASA's Goddard Space Flight Center, and I am very happy that we are finally on our way into space to begin a new journey with the X-ray imaging spectroscopy mission. I want to congratulate JAXA and the rocket team at Mitsubishi Heavy Industries for getting us this far. This took an enormous amount of work, and my colleagues at NASA are extremely grateful and wish to congratulate them on their success. Astronomers from around the world have eagerly anticipated the launch of Xrism and the new capabilities it will provide for high-resolution spectroscopy and wide-field imaging. We are now a major step closer to exploring the universe in X-ray light with a powerful new tool to reveal what is going on in so many celestial objects in our galaxy and all the way out to distant clusters of galaxies that are emitting X-rays due to their extreme temperatures and energetic conditions. We will soon bring this new observatory online and get to work. So congratulations and go Xrism team.
Xrism project principal
I am Tashio, principal investigator of the Xrism project. Tenma in the 1980s, ASCA in the 1990s, and Astro H in the 2010s. With their then state-of-the-art spectrometers, Japan always led the world in X-ray astronomy. This time again, the world's best spectrometer will be launched into the space. We are determined to use Xrism to capture the world's best spectrums to lead the world in X-ray astronomy. Please continue to support our mission.
The first video was by Dr. Richard Kelly of NASA, and the second was Professor Tashiro, principal investigator. Now we will be discussing Xrism in more detail. From Xrism project scientist Professor Matsushita, and from science operation team Dr. Shiratsu are with us. And about Xrism science research, I would like to ask of them. First, Professor Matsushita.
Relembrando que a separação do satélite Xrism do caso da carga Xrism já foi realizada com sucesso.
Validation systems will be deployed, and so we will have to continue to be watching carefully. But first step was successfully done. 3 months after, scientific observation will be carried out, and we would like to be able to report the first light. About Xrism satellite, I would like to explain. Can I have a slide? And Dr. Shiratsu, please explain about the Xrism and detector. I would like to explain. Can you see the slide? Is the slide being shared? Xrism length is 8 meters, about 3 stories high, and 2.3 tons is the mass, and width is 9 meters when solar panel is deployed. height is 550 kilometers, and it's at inclination of 31 degrees, and period is 96 minutes. From the space, X-ray arrives to the left top part of the satellite and will come into the satellite. In this cylinder, there is X-ray telescope. Using X-ray telescope, X-ray will be gathered. The focus of the telescope, the right bottom area, have two detectors. First is X-ray microcalorimeter resolve. Resolve uses freezing systems, including liquid helium, and cooled to negative 273.1 degrees. And at super high resolution, X-ray will be observed. Next is X-ray CCD camera extend. In comparison to resolve, extend has wider angle and will be able to observe an area of a sky equivalent to a full moon at a time. Using these two equipments, observation will be carried out.
So, from my side, the scientific research plan of Xrism, Dr. Shidatsu will give the latter part of the explanation. Then if you go to the website, you can see how to see the cosmic winds. How should I give the explanation on this? This is the topic I would like to talk about. As has been already explained, the telescope and detectors are on board. And what is X-rays? This is the starting point. X-rays are part of the electronic magnetic waves, like the ultraviolet as well as the lights. They are part of the electromagnetic waves with the high energy, with the short waves. X-rays cannot penetrate the atmosphere, and so the satellite is essential for the observation. As has been already explained, 1 million degrees and the 100 million degrees, the objects will be able to be observed by this X-ray astronomy. There are two detectors on board. The first one is resolved. This means the resolution and also determination. So these two things are contained in this term. Now let us compare the performance. As you can see, this is about the Astro H observation results. Perceives the clusters of a galaxy, X-ray spectroscopy, and you can see the colors in the X and Y axis. You can see those are the two detectors that are going to onboard and similar to the ones that we have. The black represents the Astro H microcalorimeter, and the red one is a Suzaku CCD. The microcalorimeter, if it is going to be used, X-ray color, that is the axis, you will be able to see how accurate it is. And similar to the sound, when it comes to the light, it is affected by the Doppler effect. If it is approaching, and then the blue shift, and then if it is going distant, red shift. And this is going to be applied to the observation. X-ray color can be observed accurately, and you will be able to see the sources, or like the high temperature gas, and can be analyzed accurately. And on top of that, you can see chromium and manganese. Those rare elements, they are going to be X-ray emissions, as you can see in the chart. Those the minor the X-rays can be detected for observation. And then X-ray based space. How is it going to be observed? When it comes to the Milky Way, you can see the near-infrared observation on the top. You can see the disk that spreads around. We are within this disk. And then X-ray has observed this galaxy on the bottom. In the bottom, you can see a different view. X-rays will use the emitted by the gases with high temperatures. In the case of the Milky Galaxy, you can see millions of degrees of X-rays can be observed. You can see the speed of the cosmic wind, and there are different the celestial objects. They are called supernova remnants. those two remnants, the left one is about 300 years ago. It is the remnant of the supernova explosion, and it's 16 light years wide. And on the right-hand side, 11,000 years ago, there was the explosion, and 250 light years expanse. So you can see the effect of the explosion. Xrism will be able to observe X-rays emitted from those supernovas, and then we will be able to observe the elements and the speed of the gases. In fact, around ourselves, when it comes into those elements, they are produced in the supernovas. And as you can see, we will be able to analyze the alchemy of the space and the speed of the wind and the evolution of the galaxies. We will be able to detect them. And you can see this round object. These are the clusters of galaxies. Hundreds of galaxies are going to be combined together. And you can see this is the enlarged picture, X-ray picture, which is enlarged, and about 600 billion years away, with the expanse of several light years. And they are trapped in the high temperature gas in the core. And most of the elements in the space are produced and then exist in the form of a high temperature gas. Xrism will be able to detect these objects, and then how those objects are growing in the space-time. They will be able to be observed. And there's some percentage of the elements that were produced in supernova are spreading around, and we will be able to observe them. In the core of this stellar object, this is M87. And this M87, this X-ray picture can be captured on the left-hand side. From the galaxy, there is a high temperature gas is emitting. And on the right-hand side, this is the microcalorimeter, which captures the spectra, which is expected to be captured. The pinkish, the dotted line, represents the Suzaku results. And you can see different kinds of information, the data can be captured. A Xrism satellite will be able to observe the emissions of those gases from M87. Then, how's the wind blows from this place?
Yes, thank you. Shiratsu speaking. M87 was just mentioned. In the center of the image of the galaxy, in a white square, that is the center of the galaxy. In X-ray, we can see that it is very bright. And if this is enlarged further, it is about 6.5 billion solar mass. There is a supermassive black hole. It is known to exist. And such supermassive black hole is estimated to be at the center of each galaxy. Other than supermassive black holes in the universe, there are various black holes, including small and large ones. For example, at the right side, this is a different galaxy, and visible light and X-ray are superimposed. And looking at this, other than at the center of the galaxy, there are some bright spots under X-ray. And this is also a black hole, and these are paired black holes. And these are several tens of times larger than solar mass, stellar mass black hole. And these are circling each other in a very short distance. They are attracted by the strong gravity of the black hole, and they are falling into black hole as they encircle, creating a disk at the center. And the gas temperature is as high as 10 million degrees, emitting very strong X-ray, and that X-ray is observable in the image above. There are small and large black holes. They not only absorb things, but as Professor Matsushita mentioned earlier, high-speed gas is emitted. For example, on the left side, this is a jet, and light velocity is 300,000 kilometers per second. Speed is as fast as that, and the falling disk above that, there is a wind emitted, as shown on the right side. The velocity of the wind is several hundreds of kilometers to 10,000 kilometers per second. Earlier, rocket, when Xrism was separated, it was traveling at about 8 kilometers per second. In comparison, the speed is much, much faster. And in a supermassive black hole, these jet or wind are emitted, and surrounding stars and gas may be moved and affect the formation of the galaxy itself. That is the estimate. But why do jet and wind come from the black holes? And to what extent do they affect the surrounding environment? That is not fully elucidated. With Xrism, we hope to be able to understand this mechanism. For example, as shown at left below, around the black hole, there is a wind, and let's say we observe this wind. Near the black hole, there are various types of X-rays with different levels of energy. And X-ray, the gas coming out, if we observe the wind, we can look at the element such as iron that will be absorbing a certain level of energy. And as shown on the right side, we can see a spectrum of absorbed energy. The wind is moving, and due to Doppler effect, from the original energy level, absorbed energy is observed at a little different time difference. And with that, we hope to be able to estimate the level of energy. And the black line showing absorbed energy, we were able to have very rough idea, but with the resolve on Xrism, each line of absorbed energy can be understood more precisely to understand the intensity and absorption of energy, how much gas at what velocity are emitted to the surrounding environment, and how much it is affecting the environment. We hope to understand that better. And with X-ray observation, time-space distortion may be understood. That is also hoped. Near the black hole, because of theory of relativity of Einstein, there is a distortion of time-space, and EM wave that is emitted will be observed with a distortion. The right side diagram shows the iron light line emitted from the black hole, and there are several peaks spread over widely. And this spread shows the distortion of the timeline. By understanding the shape of the emission line, we should be able to understand the degree of distortion of time-space around black hole. And black hole rotation, the faster the rotation, the effect is larger, and the range will be spread wider. So by understanding this, we should be able to measure the speed of the rotation of the black hole. Not only near the black hole, but at a distance from black hole, there may be a gas and wind that are absorbed. Then smaller emission lines and absorption lines will be mixed. With the existing equipment, it was difficult to distinguish, but with resolve, as shown in red line, various different components can be separated to understand the distortion of time-space around the black hole in more precise way. That is the hope, and in this way, so this is only a part of what we are hoping to achieve with Xrism. We would like to understand the mystery, unravel the mystery of universe using Xrism.
Thank you very much. And having listened to your presentations, Xrism has a very fancy name given to. The resolve means the dissolution, and then resolve also means determination and fortitude, and then extend. This represents extension of the idea, so to speak. Similar to Xrism, well, as captured in Xrism, how do you come up with the specific naming? Microcalorimeter, Rich Kelly, Mr. Calorimeter, AK, who has named this machine with the instrument in that way. Thank you very much. And the viewers probably are most interested in this topic, the distortion of space-time and black holes. And it is going to go up into 10 million degrees. And I am a scientist on the solar system, and then the temperature is like 1 million degrees, but it goes up into 10 million degrees. The flare is supposed to be the reason for this kind of creation. But in terms of the theory, do you have any specific ideas when it comes to the black hole, the temperature surrounding it? The gas comes down, declines, and it resolves and rotates at a huge speed. And then, as a result, the temperature goes up to 10 million degrees. So there is this theory, but theory is going to be corroborated and by the specific observations and by the result or the Xrism. And that's the process, and that the scientific mission is going to be made as for Xrism. Thank you very much and for your talk. Next, Slim.
I would like to introduce Slim to you, and we have a video message from the project manager. So please take a look together with the video introduction of the project. Hello to everyone watching this live streaming event. I am Shinichiro Sakai, project manager of SLIM, Small Lander for Investigating Moon. I think you're all watching the live streaming with much excitement, waiting for the launch of SLIM. I feel the same. It has been 7 years since the start of the project. If you go back to when the idea was originally conceived, it has been more than 20 years. With the support of many and efforts of all those involved, we are now welcoming the day of the launch. We have dedicated so much efforts and great deal of thinking in SLIM, with which we aim to achieve lunar landing with unprecedented precision, to open the door to the next generation of lunar exploration. We are determined to stay focused even after the launch. From the era of landing where we can to landing where we want. Please continue to support us. From Professor Sakai, project manager, we have heard a very strong message, and we have Professor Mori, who is a member of SLIM project, and Professor Otake, payload manager. We are still watching the launch sequence, but how do you feel? Project manager Dr. Sakai said that from the era of landing where we can to landing where we want, that comment was mentioned. I think this is a symbolic phrase of the landing by the SLIM. Lunar exploration in the future will lead to leading-edge observation, and for long-term sustained observation, precise pinpoint landing is essential. And SLIM will be taking on the challenge of precise pinpoint landing to open a new era. Thank you. Pinpoint landing was mentioned, and we will come back to this point later for more detail from Professor Mori. But Professor Otake, would you like to comment? Yes. Watching Sakai-san's video once again, and watching after the SLIM video, I'm also feeling the renewal of my determination, and I also feel a great deal of excitement. And as Professor Mori mentioned, pinpoint landing from scientific viewpoint is very important. Where in the moon, what geology exists. To an extent, we understand that, and we therefore have a place in mind where we would like to conduct research. And in a targeted location to achieve landing is very important. Researchers are hoping to land on some precise point, and that is known because of the past missions. You know the distribution of substance in certain areas. So in the next mission, there is a more precise targeted location for landing that is being aimed at by this project. So we would like to ask more about that later.
Now, there are some questions about SLIM. We have received them. On the back, you can see the model. Let us use this model to ask questions. The one thing I would like to ask of you is that this body, on the left-hand side, this triangle, cone-shaped, silver dent, what is it? This is antenna, S-band antenna. There are several of them, as a matter of fact. And so at whatever directions, the vehicle will be able to be engaged in communication. And thrusters as well, which are attached. And I will come back to this point later on. So on the back, on the right-hand side, so the small-sized components are gas thrusters. The brown one is the main engine, and smaller ones are 22 Newton small-sized thrusters. So they are going to be combined together for landing operation. Thank you very much. And that is the answer. This is the S-band antenna for telecommunication. Thank you very much.
We have another question. Maybe I should ask this of Professor Otake. Do you yourself would like to land on the moon? And if so, what would you like to do on the moon? Yes, I would very much like to visit moon. That is the place that I would like to visit the most. And if I'm on the moon, because I study rocks, as I mentioned earlier, I would like to bring back rocks to analyze further. There are many rocks I would like to bring back. So I would like to collect rocks more than I can carry and analyze them as much as possible. Moon scientist would like to go to the moon, but as a solar scientist, if I visit the sun, I will be burned. It's difficult to visit the sun.
I think the separation of a SLIM is going to take place soon. So we will switch the camera to Tanegashima Space Station.
Tanegashima 宇宙センター竹崎総合司令塔から H2A ロケット47号機の打ち上げ実況放送を再開します。
This is a live coverage of the H2A launch vehicle number 47 from Takesaki Range Control Center at JAXA Tanegashima Space Center.
ロケットの追尾は再開されており、現在ロケットは完成飛行を続けています。
We have restarted tracking the H2A. The launch vehicle is currently in a coastal state.
下部衛星フェアリングが分離していることを確認しました。
We confirmed that the lower payload fairing has been jettisoned.
第2段エンジン第2回燃焼開始。
The second stage engine ignition for the second time.
第2段エンジン第2回燃焼停止。
The second stage engine cut off for the second time. Separation.
SLIM の軌道への投入を確認しました。
SLIM has been inserted into the orbit.
これをもちまして H2A ロケット47号機によるクリズムおよびSLIMの打ち上げ実況放送を終了いたします。
We will now conclude our live coverage of the H2A launch vehicle number 47 with on boards Xrism and SLIM.
は
As you have watched, SLIM, Smart Lander for Investigating Moon, is separated to move on to the planned orbit. As you saw the applause, I think we are, relieved by the fact. And first, Dr. Mori, over to you.
Can you show the slides? Not these slides. So about SLIM, I would like to introduce SLIM. The mission of SLIM are twofold. First, as shown here, achieve a pinpoint landing on the moon to demonstrate that technology, and that is landing where we want to land. And the precision of landing on the moon was within the range of few kilometers to 10 kilometers, but we would like to make that more precise to about within the range of 100 meters. The key technologies are image-based navigation and navigation guidance and control. As for vision-based navigation, you may know of this from Hayabusa 2. Astronomical bodies will be captured in images, and based on the characteristic features such as rocks, the spacecraft will know its own position, and this is applied for the first time for the moon. What is different from Hayabusa 2 is that SLIM also has autonomous navigation guidance and control function. Hayabusa 2 was landing on an asteroid with a microgravity and was able to approach asteroid slowly. However, in case of SLIM, Hayabusa 2 was able to approach slowly, and operators manually were able to check the photographs and give command to Hayabusa 2. But in case of SLIM, gravity is larger, significant on the moon, and it will be falling very fast. So SLIM cannot wait for the command and will have to make its own decision. That is the major difference. Another difference is because of a significant gravity in case of the moon. Once descent starts, there is no redoing. In case of Hayabusa 2, several attempts were possible. After rehearsals, the landing took place, but this time there is only one opportunity. That is also a major difference. And the second objective is demonstration of a lightweight lunar explorer computation system for chemical propulsion, or rather chemical propulsion system and computation system will be tested. These will be made as lightweight as possible so we can carry more payload. Please take a look at the video of the SLIM mission. So there was an applause earlier after the successful separation of the SLIM, and SLIM itself will be flying. It will use Earth swing by and lunar swing by, and tidal force of the sun will be used to save fuel to arrive at lunar orbit. And as I mentioned before, vision-based navigation with a camera will be used to detect a crater to know its own position, and thruster will be used to lower the altitude. And this is motion descent, powered descent. And then attitude will be upright to vertical position. Landing radar will be used for safe landing. At 50 meters altitude, photographs will be taken to detect obstacles and search a safe area to land autonomously. And it will be moving to safe landing position autonomously. Right before landing, small probes will be released. And SLIM itself will be landing in two-step way. In this way, it will land. We hope to be able to see this. photographs will be captured by what we call Lev 1. It not only will take photographs, it will be hopping, so that experiment is planned. There is another one, Lev 2. This is the size of baseball, and it will change its form, shift its form to move about the surface of the moon. And the SLIM will also be conducting optical observation. Why do we have to have pinpoint landing? In the past, on the surface of the moon, many landers have landed, including by the former Soviet Union, the United States, China, and India just a couple of weeks ago succeeded in landing. In case of the former Soviet Union, 2 weeks ago they attempted, but were not successful in landing. And in this landing, wide, safe area, large sea is selected for landing. So landing precision can be within the range of few kilometers to several tens of kilometers. But Kaguya made a difference. Kaguya was launched in 2007 on a lunar orbit, and NASA launched Lunar Reconnaissance Orbiter. High-resolution lunar observation data is now available in large volume, and now there is a need to do a research of a certain rock near a certain crater in lunar exploration. This requires precision of about 100 meters in landing. About a SLIM lander, this is the overview. First, the weight is very light, 700 kilograms. This is about as heavy as a light vehicle. 3/4 is propellant. Excluding propellant, it is 200 kilograms, very light. And salient feature is the tank. Usually we have separate tanks for fuel and oxidizer, but this is an integrated tank for the fuel and oxidizer. And this is also the main main body, or various things are attached, including thin film, solar panel, and camera, main engine, and thrusters are attached to the tank. That is the structure of the SLIM. This is the trajectory of SLIM. As much as possible, fuel consumption will be minimized. So solar swing by, Earth swing by, and lunar swing by will be used. Also, solar tidal force will be used. Towards the end of the year, we expect the spacecraft to be on the lunar orbit and eventually land. This is the landing sequence. From 15 kilometers of altitude, motioned powered descent will start. And with autonomous navigation, guidance, and control to targeted location, lander will approach. And at altitude of 7 kilometers, it will upright to vertical position and will also conduct observation. And at 50 meters altitude, it will detect obstacles and will eventually land. And this descent phase is about 20 minutes. This is 20 minutes of terror. We believe we will be very nervously watching this 20-minute landing phase. The landing area is a slope. And so rather than landing on the landing gear, it will be a two-stage landing to change the attitude from upright to horizontal. So I would like to show you how this will be done. You have something mysterious in front of you. This is the mock-up of a SLIM, model of SLIM. This is a slope. This is a representation of a sloped lunar surface, and it will land in this way. It's actually two-step. Main gear will land, and after that, the front gear will land to take horizontal orientation for safe landing. Pinpoint landing on a targeted location. In addition, it will be landing on a slope. And inclusive of that, we would like to achieve landing where we want to land. Thank you.
So, given the name slim, a narrow shape can be considered. But when it comes to the attitude for landing, it is supposed to be a boxy style and lightweight. And then it is going to be, each gear is going to be used for the smooth landing. Right. That is the landing operation. So it is completely different from the conventional landers. The size-wise, it is much smaller. So if you take a look at all the details, it betrays the conventional wisdom. So it is going to land where we want to land. And that is supposed to be the prerequisite requirement. And then I would like to hand over the microphone to Dr. Otake for the reason why we are going to land that specific place. Now, I would like to talk about the scientific purposes. The moon itself, it was formed from the giant impact. Speaking of the giant impact, there were celestial objects, including the dirts, and then they collide each other and grow in size. And after that growth, according to the computer simulation, you can see the collision. The two objects collide with each other, and the debris after that spread out in the space. And then those debris will be collected to form a moon, and that is the result of the giant collision. But what is important is that at the time of the formation, is it made of the Earth itself or the colliding object? We have to understand which one is going to be the reason. By understanding this fact, the colliding object and the Earth, now the ratio of the size of the two objects, and the conditions of rotation, we will be able to have all the detailed information. What is important to understand this is that the giant impact that would take place in the other space-time, we will be able to have a guess. And by doing so, the Earth-like planet, how easy this kind of a planet created. And for this to be studied, first, the colliding object and the Earth, which one is going to be the first? We have to study that. And for that to be achieved, the way we are going to do the study is to compare the elements and the composition of the elements. And what is problematic in this study is that we have the crust under the Earth, and within the crust, the green area, which accounts for 90% of the volume. Most of the majority is considered as mantle, and we were not able to return them from the sample returns from the moon. Therefore, this mantle portion, we have to acquire the rocks that belong to the mantle. And according to the past studies, that it is made up of olivine. It is the rock that contains a large majority of olivine. The ratio of iron and magnesium is also going to be studied. Where we can find this kind of material, the Kaguya, which is the lunar orbital satellite launched by Japan, you can see the red dotted dots. And we have already identified these places contain a lot of olivine. So we are going to select one of those red dots, and which one is more suitable according to the topography. And we did different kinds of analysis, and as a result, we have determined a selected landing point. The area that contains this desired the rock elements is limited, and then the place is also inclined. Therefore, as Dr. Murray explained, the slim pinpointed navigation system, and then it can also land on the inclined slope. That kind of technology is essential for this kind of research. And you can see on the surface of the Earth that this is the place we are going to make it landed. And based on the research data, we have identified this place for landing, which is called Shiori, and around this place we are going to make the lander to land. And we are going to use the spectroscopy, similar to SLIM. We have developed a small-sized camera, and Professor Saiki of Ritsumeikan University is the inventor. So in this way, we have put different technologies into the small-sized camera lens, and the mirror, which is going to be rotated, and so that the scanning will be enable the lander to view the situation on the surface. And inside the instrument, there's going to be a camera to be installed, and then the observation on the surface will be done. And there are going to be 10 waves are going to be monitored and studied in order to do the analysis of different rocks, including olivine. And this is the last photograph. The two project managers are shaking hands. Please look forward to the research results. Thank you very much.
On the moon, exactly at a spot that you desire to land, and by collecting materials from there, the formation of the moon from the giant impact in the past may be elucidated to understand whether the moon is the colliding object or whether the moon was originally part of the Earth. And so you would like to land on a precise location that will enable us to collect a substance that may lead to understanding of that. And last photograph was a handshake between the two project managers, Maejima and Sakai-san, of these two projects. That was a wonderful photograph, symbolic of this project. Thank you very much. Over 90 minutes, we have been live streaming the launch today, and we are coming to the end of the live stream. Xrism X-ray imaging and spectroscopy mission will be observing stars, galaxies, black holes. Large astronomical structures will be observed to understand the formation of these structures. And small lander for investigating moon, SLIM, will attempt a pinpoint landing to understand how moon was formed. Actually, at JAXA ISAS, ahead of Xrism SLIM, there will be a series of projects and missions. For example, I myself am involved in solar observation satellite Solar C with ultraviolet. It will be able to do a very precise observation. We will have a series of these important challenging missions. The outcome of the current missions will lead to the future projects. And please continue to look forward to what we are able to achieve in these future projects. Thank you very much for watching.
The sound suppletion water system has been activated.
フライトモードオン。The flight mode is on. 同様電池起動。The thermal battery has been activated. 全システム準備完了。All systems are go. Main engine start. The main engine ignition. トルビエ点火。Lift off. Solid boosters ignited. Lift off. プリズムスリムを搭載した H2A ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H2A launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H2A has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
打ち上げ後1分が経過しました。
It's 1 minute into the flight.
70
ロケッ トは現在東方向の太平洋上へ飛行しています。
The H2A is now flying about the Pacific Ocean to the east.
83、84、85、86、87、88、89、90。
SRBA 燃焼終了。
Solid boosters have burned out.
110、
SRBA 分離。
12、
Solid boosters
13、
have been
14、
separated.
15、16、17、18、19、120。
はい、それではお時間になりましたので、本日の説明会を、開始させていただきます。本日は X 線分光撮像衛星クリズムの、記者説明会と、後ほど機体公開という形で行わせていただきます。午前中は、まず記者の皆様向けの、説明会を、実施させていただきます。本日の司会を、務めます広報部報道メディア課の岸と申します。ご参加いただきましてありがとうございます。なお本日の説明会ですが、JAXA の YouTube 公式チャンネル JAXA チャンネルで一般のライブ配信も行っております。視聴いただいている皆様よろしくお願いいたします。本日の説明会の、簡単な流れを、ご説明いたします。冒頭約30分で、登壇者から説明を、行います。その後、約30分間の質疑応答を予定しております。質疑応答の状況によっては若干の延長もあり得るかもしれませんので、よろしくお願いいたします。あと本日の資料ですが、ご参加いただいている記者の皆様向けには、プレスサイトの方で、2つ、掲載をしてございます。本日の進行をまとめたアジェンダ、登壇者の肩書き等もそちらに記載してございます。あとは本日の説明資料ですね。この2つとなります。なお、説明会終了後に、クリズムの指示画像2つ、またこの後の説明会で、ご紹介いたします、NASA イサからメッセージビデオをいただいておりますので、その動画のデータも公開を掲載いたしますので、ご活用ください。その他、本日先ほど申し上げた通り、午後には、機体公開をさせていただきますので、その時の様子を撮影した画像、映像、動画につきましては、本日夕方ぐらいを目安にですね、 同じくプレスサイトに掲載する予定となっております。掲載ができましたら、改めて報道メディアの皆様にはメール等でご案内いたしますので、よろしくお願いいたします。それでは本日の登壇者2名を紹介いたします。まず、JAXA 宇宙科学研究所 X 線分光撮像衛星クリズムプロジェクトチームプロジェクトマネージャー前島博則です。続きまして、プリンシパルインベスティゲーター田代誠となります。はい、それでは早速、前島プロマネの方にマイクを渡したいと思いますので、よろしくお願いいたします。
ご紹介ありがとうございます。ご紹介いただきました、JAXA 宇宙科学研究所クリズムのプロジェクトマネージャー前島と申します。本日は我々の衛星を紹介できることになりまして非常に嬉しく思っております。よろしくお願いいたします。本日の説明なんですけれども、私と隣にいる田代先生から、行わせていただきます。まず最初に前島の方からクリズムのミッションの概要についてご説明をさせていただいた後、田代先生の方から科学的なところを説明をしていただこうと思っております。それでは、スライドを共有いたします。ちょっとお待ちください。はい、それでは画面共有いたしました。我々の衛星 X 線分光撮像衛星クリズムと呼びます。でこれは、クリズムというのは、この X 線分光撮像衛星というのが日本語名なんですけれども、英語で言いますと X-ray Imaging and Spectroscopy Mission の、頭文字をつなげたものです。でこれはプロジェクト立ち上げ当初に、アメリカと日本とアメリカとで、協議して決めた名前でして、このミッションの性格をよく表しているということと、それとこれ X 線の分光をするというのが大きなミッションになってまして、分光というのはプリズムを使ってよく太陽の光を分光するというのがあると思うんですけれども、そのプリズムとよくかかっているというのも選考の理由になりまして、我々クリズムというふうに命名をいたしております。それでは、本日の目次構成なんですけれども、最初に私の方からクリズムのミッションについてご説明して、その後で田代の方からクリズムを目指すものということでご説明いたします。ではまずクリズムのミッションについて。これ最初イントロですけれども、まずX 線天文学についてなんですが、非常に歴史の浅い、学問の分野です。60年に満たない分野です。しかし、ブラックホールや中性子星、銀河間の高温プラズマなどを観測して、新しい宇宙の姿を世界に提供してきた分野ということになっております。クリズムも X 線を観測するという天文衛星になっています。でクリズムのミッションは2016年に運用停止した X 線天文衛星アストロ H が担っていたサイエンスである超高分解能 X 線分光による宇宙物理の課題の解明、これを早期にかつ確実に回復するということで立ち上がりました。アストロ H の開発成果を最大限活用して NASA、ESA、国内外の大学研究機関との協力をもって最先端のサイエンスを高い信頼性を持って達成するということを目指しております。で定常運用に入りましたら、クリズムは世界に開かれた汎用 X 線天文台となります。そして、宇宙の構造形成と銀河団の進化、などなど、これ後ほど田代の方からご説明いたしますけれども、こういったところを目指しまして、さまざまな分野にわたる宇宙物理をさらに推し進めて、2020年代の物理学の広範な発展の一翼を担うというところを目指しております。続いて、衛星の初言を示しております。後ほど、クリーンルームの中に、入っていただいて、衛星の実物をご覧いただきたいと思いますけれども、こちらに模型も示しております。こちらの衛星の長さ方向、下から上に、渡って、これ、おおよそ8メートルございます。非常に大型の衛星になっています。で、パドルのティップトゥティップ、パドルの端から端まででおよそ9メートルあります。午後ご覧いただくときには、このパドルは収納状態になっておりますけれども、衛星を後でご覧いただければと思います。質量は、推進薬を含んでおよそ 2.3 トン。で、打ち上げた後、軌道の高度は約550キロの円軌道を回ります。で周期、傾斜角は31度。で、周期が約96分という軌道を回ります。 それで、すでに、公開されておりますけれども、小型月着陸実証機 XRIM との相乗りで、打ち上げられる予定です。開発の経緯ですけれども、2017年から開発スタートしております。ミッション定義審査 MDR と呼んでおります審査に始まりまして、設計を進めて、その進捗に応じて各種審査会を実施しております。それで2023年、今年の3月に開発完了審査というものをもって、開発を完了し、種子島宇宙センターに搬入をしようとしているという経緯です。で、搭載ミッション機器について紹介をいたします。ミッション機器と呼んでおりまして、我々3種類ありますけれども、まず X 線を集める望遠鏡を搭載しています。これが、X 線望遠鏡 XMA と呼んでおりますけれども、こちらは、分担して開発しておりまして、NASA が開発を担当しております。でこれが、我々検出機を2台積んでおるんですけれども、それぞれについて専用の望遠鏡ということで2台搭載しています。これが衛星の上部に搭載されています。で、ここで天体から来る X 線を集光いたしまして、この衛星下部に搭載している検出機に、X 線を導入いたします。で、我々の検出機は2つありまして、1つ目が南 X 線撮像装置、エクステンドと呼んでおる検出機があります。これが、CCD、X 線に感度を持っている CCD を使いまして、X 線の撮像を行う、ミッション機器です。で、もう1台が南 X 線分光装置、リゾルブと呼んでおります。こちらの方がマイクロカロリメーターという非常に高度な技術を用いておりますけれども、これで X 線の分光を行います。X 線のエネルギーを分別いたしまして、波長分解能、非常に高い波長分解能を持っておるんですけれども、これで分光観測を行うというもので、我々のXRISM衛星のメインミッションになっております。これらをもって、X 線の観測を行うというような衛星の仕組みになっております。続いて、開発運用体制についてご説明をいたします。JAXA が NASA、ESA と覚書を結んで進めている国際共同プロジェクトとなっておりまして、特に NASA とはジョイントプロジェクトとして位置づけられております。でこれで、JAXA と NASA の間でプロジェクト全般にわたって密接に協力しながら進めているプロジェクトになっています。これら3つの宇宙機関だけではなくて、日米欧それぞれの大学、研究機関、企業から衛星開発、観測装置やデータ処理ソフトウェアの開発、さらには科学的な観測計画の策定のために100名を超える宇宙物理学者、技術者が参画をしております。で観測されたデータなんですけれども、NASA とともに検証処理され、検証済みサイエンスデータとして研究者に公開されることになっております。地上局のネットワークについて、我々の衛星の追跡管制運用なんですけれども、JAXA が持って、国内外に持っておる地上局に加えて、NASA が有しております地上局も使わせていただいて、我々は追跡管制を行います。で、NASA 局を使うことによって、我々国内、我々の JAXA の局だけでは、見えないところまで可視を広げることができますので、これで、より衛星の状態監視を強化することができます。続いて衛星バスについてご説明をいたします。まず構造設計のキーポイントなんですけれども、精度よく目標天体に飛行させる必要が観測上ありますので、熱歪みが非常に低い構造材料を使用しています。それをもって、さらに、軌道上で環境変化に対して高い形状安定性を実現するべく、光学ベンチの上に、X 線望遠鏡を搭載しているというのが特徴になっています。先ほど申し上げました、X 線の望遠鏡ですけれども、これがこの熱歪みの小さいような特性を持った設計をしたベンチの上に乗っかっておりまして、これで、軌道上の熱変化に対しても動きが小さくなるような設計としております。それで、正確に衛星の下部、ベースパネル上に搭載している検出機に、X 線の焦点を合わせるというような設計になっています。続いて、熱設計ですけれども、キーポイントは、機器の発熱は熱歪みを嫌う光学ベンチおよびベースパネルに流さないで、側面パネルのラジエーターから排熱をするというような設計をとっています。でそれの熱の輸送のためにはヒートパイプを使用しております。でこれで、熱の歪みを嫌うところに熱を流すことなく、しかるべき排熱のパスから熱を逃がすというような設計をしています。それと、ロバット製の設計を我々取り入れておりまして、アストロ H からスラスター噴射異常対策機能を追加するなど、ロバット性を向上しているというところが一つのキーポイントになっています。 アストロ H の軌道上の異常事象を受けまして、我々、いくつかのロバスト性向上策を取っております。で、その中で一番大きなものは、スラスタ噴射異常対策機能というものがありまして、これは、軌道上で、万一スラスターが5噴射を起こして、衛星が回転を始めたときに、衛星が自律的にその回転を検知しまして、ある一定以上の回転に達したときに、衛星が自動的にスラスターの噴射を止めるというような機能を付加しております。で、これをもって、さらに、安全性を高めるというような設計をとっています。続いて、X 線望遠鏡について、ご説明をいたします。X 線望遠鏡 XMA は、天体からの X 線を集光する機能を有して、リゾルブと X 線度それぞれに専用2台搭載されています。で、X 線はその、物理的な性質上、滑らかな物質表面に1度以下で入ってきた場合に、のみ反射すると。ご存知の通り、X 線はレントゲン等で、物を透過する力が強いということはご存知だと思うんですけれども、非常に浅い角度で入ってきたときは、反射をするというような特性を持っています。ということで、いわゆるパラボラ鏡のような反射鏡ではなくて、この板を同軸状にバームクーヘンのように配置をいたしまして、浅い角度で入ってきた X 線を、焦点を結ぶというような構成になっています。で、これを利用しまして、X 線を一点に集めるというような設計になっています。で、構造なんですが、203枚の薄い反射鏡シェルを同軸状にレコに配置して、合計45センチ、標定距離 5.6 メートルの望遠鏡を構成しています。で、続いて、メインのミッションです。リゾルブと呼んでおります難 X 線分光装置です。XMA、X 線望遠鏡の焦点に、画素が 6×6 の画素を有しておりますけれども、X 線マイクロカロリーメーターアレイと呼んでおります精密分光器です。で、これはこれまでにないエネルギー分解能を達成することができておりまして、0.3 から12ケブの広い観測帯域において、これまでにない分解能で観測を行います。で、マイクロカロリーメーターは検出器に入射した X 線の光子一個一個のエネルギーを素子の温度上昇として、測定するというメカニズムを有しておる検出器になっています。で、これはごく低温にして性能を初めて発揮するシステムになっておりまして、断熱生じ冷凍機、強流動ヘリウム、機械式冷凍機、これらを格納する真空断熱容器、これによって検出器をマイナス 273.1 度、これは絶対温度にして 0.05 度に相当するんですけれども、このごくごく低温に冷却することで、超高分解の分光を実現をいたします。で、この装置は日米欧の協力開発となっております。で、もう一つの観測機器、ミッション機器、難 X 線撮像装置エクステンドですけれども、こちらは、CCD カメラと同じような原理でして、難 X 線に感度を強く持っているというような CCD を開発しております。で、厚い空洞と、裏面照射型の CCD を採用して、従来の X 線 CCD より高いエネルギーの X 線検出、低エネルギー X 線に対する高い量子効率を達成しています。で、X 線望遠鏡としては、これまでにない、最大の視野を持っております。38分割四方という視野を持っております。で、これで満月より広い視野を一度に観測可能というのが売りになっています。で、大きく広がった天体の観測で力を発揮するほか、リゾルブの視野外の天体を捉えることで、リゾルブの観測をサポートするというような役割も担っています。で、ミッション運用、科学運用について、ミッション運用ですけれども、JAXA の内之浦宇宙空間観測所を主局といたします。先ほど国内外の地上局を用いて、追跡管制運用を行うというふうにご説明をいたしましたけれども、ミッションデータの伝送については JAXA の内之浦宇宙空間観測所を主局として行います。それで衛星状態の記録、データの再生、衛星制御コマンド送信などを行います。で、NASA 局も使用して状態監視を行います。で、衛星自動監視システムと呼んでおりますけれども、これは、我々、衛星から送られてきたテレメトリーをモニター画面を通して運用者がチェックをするわけなんですけれども、衛星自動監視システムというものを導入しておりまして、これで、機械的にテレメトリーの中の異常を早期に発見するというものを我々取り入れておりまして、これを実用で使います。で、続いて科学運用についてですが、JAXA、NASA、ESA が公募して採択した観測提案を一つにまとめて、JAXA にて日々の運用計画として詳細化いたします。 で、観測されたデータは JAXA にて、天文学標準のデータ形式に変換されて、NASA にて構成処理が施された後、日米で配布保管されると。で、それで、科学者に提供して、解析を行っていただくというような流れになります。計画に参加している期間、ここに一覧、ちょっと小さい字で申し訳ないですけれども、JAXA がリードをいたしまして、NASA とジョイントプロジェクトという形で進めております。で、ESA が参画いたしておりまして、協力をして、開発を進めております。で、その他、国内外の大学、あるいは、研究機関、など、このようなたくさんの機関に参加していただきまして、開発を行っております。で、運用段階でも協力をしていきます。で、こちらに、衛星組み立て試験の様子の写真をいくつか、示しておりますけれども、一番左側に示しておりますのが、これが、衛星の音響試験の時に撮った写真です。衛星システムの組み立て試験は、筑波宇宙センターにて行いました。で、こちらの大型の試験設備を使いまして、一連の機械環境試験を行ってきております。それと、真ん中の写真は XMA、ミラーの組み付けの状態を示しておりまして、これが衛星の上部ですから、非常に高所の作業になりますけれども、衛星の周りに櫓を組み立てまして、足場を組み立てまして、そこで、注意深く衛星の X 線の望遠鏡を組み付けているという様子の写真です。で、右側の2つですけれども、リゾルブ、あるいはエクステンドの単体の試験の様子を示しております。で、今後の予定です。今、車上整備作業を行っておるところなんですけれども、この後、水薬充填という重要な作業が始まります。で、水薬充填をした後、フェアリング結合、ロケット結合を経て、打ち上げに向けての準備を進めてまいります。で、打ち上げた後なんですけれども、初期段階として我々3ヶ月を計画しています。で、その初期段階は2つに分けておりまして、クリティカル期間とコミッショニング期間。クリティカル期間では、姿勢、電力、通信などの衛星の基幹機能の確立を行います。それと、ミッション機器の一つ、南 X 線分光装置リゾルブの冷凍機の定常運転まで持っていきます。で、コミッショニング期間では衛星の基本機能、性能の確認を行います。で、それが終わった後に定常段階に入ります。で、この衛星は打ち上げ後3年が設計寿命になっておりまして、初期段階を除く定常段階は33ヶ月という計画になっておりまして、その中の最初の7ヶ月は初期構成検証期間と称して、ミッション機器の構成、性能検証を行う期間になっています。で、それがすべて完了した後は、ゲストオブザベーション期間と称しておりまして、定常観測、天文台として、活躍するような期間となっております。以上が、クリズムの、ミッションの概要のご説明となりました。それでは続きまして、田代の方から、クリズムの目指すものというところでご説明引き続きさせていただければと思います。
では引き続いて、ミッション PI プリンシパルインベスティゲーターの田代から、クリズムの目指すサイエンスについてご説明いたします。プリズムは X 線で宇宙を見る装置ですけれども、X 線で宇宙を見るというのはどういうことかというのを最初に概説させていただきます。20世紀に入って様々な装置が開発されまして、それまでの可視光による天文学から電波を使った電波天文学や X 線天文学、ガンマ線天文学、あるいは赤外線天文学と様々な波長の電磁波の天文学が進歩してきました。20世紀はそれらが百花繚乱開いて、新しい今まで見てなかったような宇宙を見た時代ということが言えます。こちらが可視光で撮った銀河系の写真です。同じものを、これは最新の X 線で撮った、X 線天文台でありますイーロジータで撮った写真になります。こちらでは星がキラキラと輝く割と静謐な感じの宇宙をイメージしますけれども、こちらでは何かが吹き上がっているような非常にダイナミックな宇宙が見えてきます。で、この違いというのは X 線の性質に由来します。光に対して X 線は波長が短いということは一個一個の光子のエネルギーが高く、X 線を出すような物質というのは温度にすると1000万度ほどの温度を持つような物質になります。この温度を持つ物質はもうプラズマ化しています。つまり電離しています。で、このような高温プラズマから出る現象が X 線ではよく見えます。このような高温プラズマが銀河にもあるんですけれども、
光ではそれはよく見えません。可視光ではよく見えません。ただし X 線は、大気を透過しません。ですので X 線を観測するためには、電波や、可視光あるいはガンマ線のように地上で観測することはできなくて、軌道上に人工衛星を使って観測装置を打ち上げ
Agradecemos por sintonizar. Até o próximo lançamento.
アメリカのジェームズ・ウェッブ、これは可視光を観測する望遠鏡ですね。可視光でもより精度を高めたり、より遠くのものを見るために宇宙に進出するものもあります。
Sleep, yeah. Only miss you when I'm breathing in too deep, yeah. Am I just your little secret? I didn't hear the sirens. I didn't wanna see the warning signs, and now I pay the price, yeah. Oh, I should've known. It hits me like a tidal wave every time you say my name. It hits me like a tidal wave. It hits me like a tidal wave. A tidal wave. Tidal wave. Tidal wave. Tidal wave. Waiting patient on the shoreline. Now you're leaving, but I know you got your reasons too. I didn't hear the sirens. I didn't wanna see the warning signs, and now I pay the price, yeah. Oh, I should've known. It hits me like a tidal